Okay, so today we're going to discuss more boundary layers and the boundary layers under pressure influence. And on Wednesday, now we're going to use the knowledge we gain on boundary layers to look at what is the effect of the boundary layers on airfoils and wings. And on Friday, we're going to be talking about flow transition from laminar to turbulence, and what is the effect of turbulence on boundary layers and wings. Okay, and we just finished the quiz 1, and just to let you know, be prepared, the quiz 2 is actually less than a month from now. Alright, it's the same deal in class, 15 minutes. Okay, so I hope you did well in quiz 1. I'll take a look this week, and I'll adjust the difficulty according to that. Alright. Okay. So how large are the forces affecting the boundary layer? So this is something I think Professor Driller already talked about last week, so I'm going to go through that very quickly. And I just want to give my perspective on it. Hopefully it's a different perspective and gives you some additional food for thought. Okay, so basically, according to the boundary layer profile, so no matter what kind of boundary layer profile it is, the slope of the velocity at the wall. So if you look at the du over dy, right, that is actually what we looked at actually 2 weeks ago. That determines how much viscous force there is, right? The derivative of velocity with respect to the y direction, the direction of change. If you multiply that, that is called the tau. Basically, that is the tau has exactly the same unit as pressure, okay, which is force per area. Okay, so this is basically the force per area of viscous force, right? The force per area of pressure force is just the P, right? The force per area of viscous force is tau, which is the viscosity times the rate of change of the derivative. Okay, so now if you look at a boundary layer, this is on the when I use the Whitley sign, that means on the order of magnitude, right? It is usually a constant that's somewhere between 0.1 and 10, right? So basically the order of magnitude times something, and this is basically u naught, the velocity just outside of the boundary layer, divided by the thickness of the boundary layer, right? So I think Professor Driller used the example of a parabolic profile. Is that the profile he used? Okay, so assuming you have a parabolic profile, this derivative is exactly twice u naught over delta, right? And of course, we also need to multiply by mu, okay? And if it's a linear profile, exactly linear, the slope is exactly going to be u naught over delta, right? If it's parabolic, it's twice that. If it's even steeper than parabolic, maybe 3 or something, but like it is some order 1 constant times that u naught over delta, I mean the derivative. Okay, so now what is the force? So the force, I mean, let's consider an area that is delta x over delta z by delta z. So delta z is in the third dimension, the dimension into the board, right? Then the force is, as I said, tau is force per area. So the force is actually tau times delta x times delta z, right? That's just, of course, is delta x, delta z times mu. Well, I shouldn't say equal. It's on the order, right? On the order of u naught over delta, right? Okay, and now conservation of momentum comes in, right? Force is equal to, there are 2 ways to look at force. For something that's actually changing as a function of time, force is equal to the change of momentum, right, over time. So that's like F equal to ma, right? But for a control volume analysis, right, for a control volume that does not change in time, what is force equal to? Just to recall, in our very first week, we look at lift, right? Right? Yeah, what is force equal to for a control volume that does not change as a function of time? Well, it is equal to the imbalance of momentum flux. So if you have momentum going into the control volume, momentum going out of the control volume, if there is no force on the control volume, then the momentum coming in should be exactly the same as momentum going out, right? But if there is force on this control volume, such as the viscous force on, well, let me just draw the control volume. The control volume is going upward and follow a streamline and then go downward. This is the control volume we're looking at. Okay, so that control volume, there is no pressure force because we're looking at a flat plate. The pressure has no influence. The pressure is uniform, right? So when there is no pressure gradient is equal to 0, there is no pressure force. So no pressure force. The only force on this control volume is the viscous force, kind of pulling this control volume backwards. So that force should be equal to the imbalance of momentum flux, right, in the control volume. So if the force is pointing towards that direction, that means there has to be more momentum coming in than momentum going out, because the force acts against the direction of momentum. All right. Okay. So now what is that momentum imbalance? So that is equal to the momentum going in minus momentum going out. So the imbalance in momentum, I'm going to skip like all this momentum defect stuff, but like the imbalance in momentum is equal to the minus of something. Well, that's actually theta, right? Theta is the momentum thickness. That is exactly describing the difference between a boundary between the. Okay, so if you assume all the mass flux into this control volume has exactly U naught, right? That's and compare that momentum flux against the actual momentum flux with the boundary layer. That difference is equal to the momentum thickness times U naught times delta Z. Actually, sorry, for momentum flux, it has the rho U squared, right? Rho U squared is the rho U squared is the momentum flux per unit area. All right. So rho U is the momentum per unit volume, right? So if you multiply the momentum per unit volume, rho U, times a height times a depth and times U again, you get the momentum per unit volume multiplied with volume per unit time, right? So 2 lengths and 1 velocity, that's volume per unit time. So what you get is the momentum per unit time, the momentum flux. All right, so that's the influx, and theta. Let's say we have station 0 and station 1. So this is theta at station 0 minus. Again, it's a minus of theta at station 1, rho U naught squared delta Z. Okay, so if you look at this imbalance, and we know that theta is actually on the same order of magnitude as delta, right? I think Professor Ritter told me he didn't cover Blasius boundary layer, but like for a flat plate boundary layer, there is a constant ratio of 2 point something, about 2.6 difference between the displacement thickness and the momentum thickness. But now if you so that thing is going to be proportional to, I would say, okay, so if you just get rid of the signs, it's delta theta, the difference in theta between downstream and upstream, times rho U0 squared delta Z. Okay, so now if you pull out this part and this part, what you get is, and you cancel out delta Z, right? What you get, and you cancel out one of the U0s, what you get is delta X times mu over delta is on the order of magnitude of delta theta times rho U0. Yes, question?
Yeah, here delta is the displacement thickness or the boundary layer thickness?
So here, it doesn't actually matter. So what I'm doing is basically an order of magnitude analysis, right? if you replace the theta with delta, right, you get basically a constant multiplier. Okay, and right. So let me actually just to write everything in terms of theta. That might be easier, right? So essentially, when I'm doing squiggly, that means there is a constant multiplier between the left and right. All right. So if you replace theta with like displacement thickness, you get a different multiplier. But like this relationship is the same. Okay. Okay. So now if you think about the delta being very small, so look at the very small length, and this you can use calculus. So what you get is right. If you multiply theta onto this one, you get d theta squared. Of course, I mean if you stick with calculus, you get over 2. But like since we are looking at a constant multiply anyway, it doesn't matter. And then there is a rho u0 over. Let me actually multiply it to the other side. Let's actually put everything onto the other side. Now this is going to be on the order of magnitude of delta x, well, dx, times mu over rho u0. All right. Do you follow the whole derivation? Yes?
Sorry, can you explain why the delta becomes theta again? Like when you have like delta
Oh,
x.
here? You mean here? Yeah, so basically theta and delta have a constant multiplier on top of each other. Right? So for a boundary layer on the flat plate, the theta is equal to a fraction like 1 over 2.6 times the displacement thickness. So when I replace, for example, delta with theta, I can basically multiply one side of the equation by 2.6 and the equation would be equal, right? So when I'm writing the squiggly sign, it's kind of an order of magnitude analysis. It is invariant to a constant multiplier of order 1. So that's why like I can replace things like that. Yes?
So when you multiply the theta to the other side, why did it combine with the delta theta? And become
Why do I combine this with that? Yeah. So basically this delta is I'm looking at any length, right? And if the length is very small and the change of x is very small, change of theta is very small, then I can use calculus, right? So basically at this line, I can still consider any finite change in x and theta. But if I restrict the change to a very infinitesimal change, then I can use calculus to get theta times a small change in theta is equal to the small change in theta squared over 2. All right. Okay. So now this equation, of course, there is a lot of math derivation, but like it actually means something important. So here we get a change in the square of the thickness of the boundary layer. Here we get a change in the streamwise distance, right? And the dimension of this is length squared. The dimension of dx is, of course, length, which means this guy has a unit of what?
1
Uh,
over length again.
it has a unit of length, that's right. All right? Okay, and if you look at this, mu is just a function of the fluid itself, right? So it's a function of air. And mu is on the order of 10 to the minus 5 if you stick to all the metric units. Rho has a scale of about 1, right? Kilogram per meter cubed. Velocity, well, it depends on what you're looking at, but like for airplanes, it's on the order of 10 to 100, right? I mean, for supersonic airplanes, on the order of 1,000. But like this is roughly 10 to 1,000. So if you do the division properly, this is a very small length that ranges from like a micrometer to like a tenth of a micrometer to maybe even for very high speed flows like a hundredth of a micrometer. Okay, and this distance actually is very critical for viscous flows in kind of judging, in your figuring out what is the relationship between the thickness of the boundary layer and the horizontal or the streamwise development of the boundary layer. Okay, so whenever, for example, you know the scale of x, which is the over what length the boundary layer has developed, you multiply that length by this small number, that constant. Let's just say, okay, it's 1 micrometer. Okay, and if you multiply the length over which you develop, let's say 1 meter, right, by 1 micrometer, and take the square root, you roughly get how thick the boundary layer is. Okay, so in just the example where we were looking at, if this is 1 micrometer, this is 1 meter, what is the thickness of the boundary layer? What is the scale of the thickness? If you do an order of magnitude analysis, exactly, it's exactly 1 millimeter, right? Because this is 10 to the minus 6, this is 1, multiply is 10 to the minus 6, take the square root, you get 10 to the minus 3. Okay, 1 millimeter thickness. So this kind of gives you a scale of what the boundary layer thickness usually is, and also how it changes when you increase the speed or decrease the speed, right? It goes like a square root. If you increase the speed, the boundary layer thickness decreases, but to the square root, okay, of the speed. If you decrease the speed, it increases, but also to the square root. And this is all assuming laminar boundary layers, and we'll discuss turbulent boundary layers sometime later this week. All right, any questions on this? Maybe you haven't seen a lot of such order of magnitude analysis before, but like I think in engineering, this is extremely useful type of analysis. Basically, looking at things, ignoring all the kind of order one constants. That is going to change the result quantitatively, but not qualitatively. Okay, so this is just one of the examples. Okay, so now let's actually use let's now get a little bit more quantitative, right? So last week, I think Professor Drayler introduced to you the different thicknesses, right? Yes or no? Do you know what is 99% thickness of a boundary layer? No? How about displacement thickness? Yes? Okay. How momentum thickness? Yes? Okay. Shape factor? Yes? Okay. So, skin friction coefficient, have you looked at this? No? No skin. Okay. So let me just explain. I mean, this is very simple. 99% thickness is very simple. So if I have a boundary layer, so this is a velocity as a function of y. A boundary layer looks like this, right? Okay. So when y is very large, I have u naught, sometimes also called ue, like e means edge, like the edge of the boundary layer. What is the velocity? And the 99% thickness is whatever y. Okay, so that's the whatever y that makes the okay. So ue is here. Ue is basically the edge of the boundary layer, and at delta 99. The velocity is 0.99 times ue. So that is basically, sorry. Yeah, thank you. Whatever distance away from the wall where the velocity reaches 99% of the free stream velocity. So, right, very, very simple. Why is it important? This is usually used to basically restrict the analysis of a boundary layer into a certain height, right? So it basically says that above delta 99, I don't care about it anymore. Like it's whatever velocity variation due to viscous effect only accounts for like 1% of the free stream velocity, right? So it is usually considered anything above this is officially outside of the boundary layer. It is almost like the definition of space, right? Above 100 kilometers, like the air is so thin, like you can ignore. You can think about like you're outside of the atmosphere. So this is like above delta 99, you can think of as if you are out of the boundary layer. All right. Okay. And displacement thickness, I just want to maybe I'll just write the equations again. Okay. So displacement thickness, it's such that delta star times UE or U0 times the velocity outside of the boundary layer is actually equal to the integration from 0 to infinity or to outside of the boundary layer. You can approximate it as if you're integrating from 0 to delta 99, right? Of UE minus U times dy. All right, that's basically that delta star essentially tells you how much the existence of the boundary layer deflects the streamlines outside of the boundary layer. Okay, momentum thickness is the following. Momentum thickness is theta. Theta is defined as theta times UE squared. So we're considering incompressible flow, but like in reality, like all of them are multiplied by rho, right? So there is a rho. Let's just think about rho as constant right now. Theta is equal to from 0 to U infinity, U times UE minus U dy, right? And the shape factor is basically the ratio between delta star and theta, right? H is that. Okay, so what is the skin friction coefficient? Okay, skin friction coefficient is defined as tau divided by half rho UE squared. Remember, tau is the skin friction force per unit area. So force per area has the same unit as pressure, right? And remember how we defined the pressure coefficient? Pressure coefficient was defined as pressure minus P infinity divided by half rho U infinity squared, right? So the skin friction coefficient is defined exactly the same way. So we non-dimensionalize this quantity, that is force per area, by half rho U squared. All right. Okay. So please come up and work out for this particular example. Consider a boundary layer that can be approximated as 4 discrete layers. Okay. What is the 99% thickness? What is the displacement thickness? What is the momentum thickness? What is the shape factor, etc., etc. All right. So this is basically to help you understand what these quantities are, what these concepts are, and if there is any misunderstanding, you're going to get the wrong result, and we can correct your misunderstandings. Chalks here. More chalks here. Chalks here. Yeah, draw the picture first. Good idea. More here.
Professor?
Yeah.
Why is it y versus u instead of u versus y? Because would your velocity depend on how far away you are from the surface of like your body?
No. Y is usually the axis like that. U is this axis.
Isn't y like the independent variable in this case?
Yeah, Y is independent variable in this case, but we are usually drawing it such that we have a wall like that, right? And if you draw Y this way and U this way, you can actually draw multiple boundary layers as you go downstream. So this is always Y, and the boundary layer may be like that, and now it becomes like that, and then now it maybe becomes like that. So basically, this makes it more convenient to draw multiple boundary layers on an airfoil, right? So So now you can draw things like that. If you flip it, then like it's hard to visualize the boundary layer as how it evolves.
Oh, I see.
Yeah. Oh, feel free to erase this. Where is the eraser?
Are we
Yeah.
going to infinity or just because this thickness is like okay?
Yes. Which question are you working on?
This one.
This one.
Yeah.
Yes, go to infinity. And basically, yeah, when you say like u is equal to 1 meters per second at y greater than 1 millimeter, that means u minus u is going to be 0, right?
Yeah.
Above 1 millimeter. So going to infinity is pretty safe. Yeah. Feel free to erase things.
I just took this thing to be one,
Yes.
and this is equal to.
Right. What is your answer to the question 1?
Oh, it should be, I think, 0.99 meters per second.
It's a thickness. Like this is yeah.
Yes, 0.99 meters.
So if you draw the profile, right, at what y would the velocity first reach 0.99 times 1 meter per second? 1 millimeter, that's right. If you draw it, yeah, because we are looking at stairs. So when you are below 1 millimeter, you're always 0.9 meters per second, right? And the moment you reach 1 millimeter, you are reaching above 0.99 meters per second. Okay. Sounds like you lost your voice.
What is this thing? Do you want to do the next one?
Yeah. So if you look at how many layers did I have? Right. So that's the profile, right? And to figure out the 99% thickness, you take this is UE, right? And this is 99% UE. You go up and see when you hit the profile. In this case, you hit the profile at 1 millimeter, right?
Oh, I was doing the second one.
I know you're doing the second one. I just they are doing the first one.
So I just didn't notice the question.
UE is the velocity outside of the boundary layer. Yeah. We call it the edge velocity because it's the velocity at the edge of the boundary layer.
Now we can do the first one.
Wait. Something like that.
So which question are you working on?
We just withdrawn.
Okay. Yep. For that one, you just the easiest way is to stick to this picture, right? So you draw a 0.99, go upwards, and see where you hit the profile. You hit it where? No, just look at the discrete profile. Exactly. Yes. Exactly. That's the right answer.
Oh, okay.
Yeah. What's your answer to the first question?
Oh, we haven't done it yet.
Oh, okay. It's fine.
Professor, can
Yeah.
I ask questions?
Yeah. Go ahead.
How are we supposed to think about number one if it's not a continuous function? It's just discrete.
Yeah, so you stick to the same way, right? So if you draw the discrete profile and the trace upward at the 0.99 UE, go upward to see where you first hit the profile.
Okay. The profile looks something like, so first there's nothing, and then it's like this one.
Yes.
So, oh yeah. So if it's I see.
Yeah.
I just had to draw it.
Yeah.
So
You just have to draw
since
it.
it's technically continuous, this is the 0.99 of the velocity. Even though it's a spike there, I don't know. I missed that.
Yeah, that's right. Yeah, they figure that out.
Yeah.
If you draw it, you figure it out.
And then,
Yeah.
To get the area, we were basically just going to represent the piecewise on a graph.
Yes,
and then
yes.
compute the area
Yeah.
that way, multiply.
So here, it should also represent it in a piecewise way, right? So to figure this out, you go from the 0.99 UE upwards on the picture to see where you intersect with the profile. So instead of a continuous profile, draw the piecewise profile and do that exercise.
Yeah.
Yeah.
Okay, we got it first.
Yeah. So this is we are using a discrete profile, right? So it's not actually several points. It's actually it's piecewise constant. Exactly. And then when you do this question, you should basically start a vertical line from here, 0.99 times you need to see where it intersects with the discrete profile.
This to be U and you want this to be what? 0.
Make sense?
Oh, so 0.9 there.
I mean, okay, we can do it.
Nope. Should be 1 exactly. Because you're at 1. Yeah.
It's just, it would just be within.
So this is not the same thing, but this U is squared.
Sorry. This is why is this 0.9? Oh, if you look at this, right? So it's UE minus U. So this would be 0.1 instead of 0.9. This would be 0.3 instead of 0.7, and this is 0.6 instead. No, this one 0.6. Yeah. Nice.
I was just going to integrate it, but it's discrete. I guess we add it.
1 second. Oh, where did you get the square thing? Wait,
This is a function of y, right? So
Yeah. So why do you get the squared? Where did you go from here to here?
Oh, cancel this. Factor. So I factored this out. Canceled on both sides.
Yeah. But how did you go from here to here? Yes. I don't know where the u square come from.
Integrating u as a function of y. This would be right.
Just like it is easier to the square, but when I
Nope. Yeah, u is a function of y, but like u is a piecewise function of y.
Oh, okay, yeah. So we're just adding that.
Yeah, you just you just working on the integral by
Yeah,
just
yeah.
adding up the pieces.
No, I see that, yeah.
Yeah.
Work down the length and thickness.
Okay. Oh, you're fast. Okay.
This is theta. Yeah. Just theta 1. So h would just be this.
Good.
This one.
You guys are fast.
Oh, is that this? Can you explain to me why they got 1 for the number?
Oh, I guess like why did you get 0.9?
Well, because the velocity right before the before it goes to 1 meter.
So I see like when you draw the red curve, right? So can you tell me like what these turning points are?
It's like the change of velocity.
Yeah, where these turning points are? Like
This is like 0.3, 0.6, and then 0.9, 0.6, and then 0.9.
yeah, that's the 1 second. Yes. Now you trace a 0.99 upwards. Where would you hit that curve? Right here. Yeah. And what is the y location for that?
It's at 1 meter.
Yeah.
Oh,
It's 1 millimeter.
okay. But wouldn't it just be just before that, though? Or I'm confused because it's 1 meter per second at y greater than 1 millimeter.
Yes.
So the 9.9 is right before that, right?
Yeah, but it's.
And we know u is 1, right? And it's like
Yeah. So if you have a continuous profile, you would basically hit that location and trace whatever y it is. But like here, we have a discrete profile. So if you do the same exercise, you're going to be hitting it at the plateau, right? Which is at 1 millimeter.
Something times delta or something.
essentially it's like right before, like
Yeah,
like,
right before.
because this is the first layer. This
Yeah.
is the first layer. This is the
Yeah.
second layer.
Yeah.
This is the third layer.
Yeah. So delta 99 is at the edge of the third layer, right?
Oh, because
The
it's
third layer is still less than 0.99 times UE.
okay. But the third layer is in between 0.6 and 1, and so we take the 1 value.
Yeah.
I see. Okay, that makes sense. Okay.
So basically, below delta 99, the velocity is less than 99% UE. Beyond the delta 99, the velocity is greater than 99% times UE.
That's what we're saying.
Sure. Okay. That makes sense.
Yeah. Okay.
Okay, I see. It's like, yeah, it'll kind of be like an average.
Yeah.
Are we integrating this from 0 to the 99?
Yeah, sure. I mean, in the definition is that you integrate to infinity.
Yeah.
But in this case, beyond the delta 99, actually delta 99, when you go up, where do you hit that velocity profile? You hit it at this horizontal line, right?
I feel like I did it wrong this time.
Yeah.
Because this is...
Yeah, and that horizontal line is at y equal to 1.
Oh, I thought you said it was like at 0.99 of UE.
Yeah, so that vertical line, the location of that vertical line is 0.99 times UE. Okay, but if you trace that line upwards,
okay.
you hit the velocity profile not at 0.99 but at 1. Yeah, that's right.
That's a number. This.
Yeah, I know, but yeah, but you're just finding this.
Yeah. So here the definition goes to infinity, but in reality, beyond the delta 99, the 1 minus u would be 0, right?
Because of the
Same here, right? Because u times 1 minus u would also be 0 here. So
Also, quick check. I just remembered. It's 1 minus this. This is, so this should be 1 minus that, and this is the area.
So 1 second. So 1 minus should be like this.
Yeah, around.
No, around this. So 0.3 is dy, right?
Yeah, but isn't it one? It's also equivalent to 1 minus this entire thing.
Yeah, he was saying.
Oh, that's right. That's right. Yeah. You can pull this one off. Yeah, exactly. Yeah.
So yeah. So then this, I got 0.69 for this.
Yeah. Yeah, that's right. Yeah, that's smart. You can pull this whole thing out. Yeah.
Okay, and then that next one. Okay, so
Looking at me? Yeah. Okay. Yeah.
The friction should be 0, no?
Well, here is a kind of an unfair question because okay, so question 5 is a little bit unfair because you have to use some kind of approximation, right? If you look at what is the derivative at y equals 0, you're gonna get actually infinite derivative because either infinite or 0, depending on how you look at it. So here we have to use some kind of finite difference approximation, right? I mean, if you fit a line through the velocity profile, then you can estimate what is the skin friction coefficient. I mean, there is no precise answer for that. You have to approximate it somehow. Yeah.
What if our theta is a constant of x? Isn't the velocity profile the same?
Oh yeah. Here I didn't. I only provided the profile at one particular x.
We don't know what is that.
Yeah, you don't know how the profile changes as a function of x.
How can we find that?
Now, how can we find that, right? So remember the equation I laid out in the beginning of the lecture. There are two sides of the equation. One side relates to how theta changes as you move downstream. The other side is directly approximated as a function of the velocity profile, right? Using du dy. So here we don't have du dy because it's a piecewise constant. But like if you fit a smooth curve through that, then you can start to estimate du dy at the wall. So try that.
At the wall.
Yeah. So basically, fit something like this. And then you can say, okay, I would just connect the middle of this vertical line with the 0 point and estimate that slope. Yeah.
We'll just try and do 5.
Yeah. Okay. Doing 5, that's exactly what you do, right? You fit a smooth curve and estimate the derivative here.
It depends how the white Sorry.
And for those who are figuring out the skin friction coefficient, the viscosity of air is this much. All right, 1.73 times 10 to the minus 5. Since we're doing approximation anyway, just to use 1 times 10 to the minus 5 is fine. All right. Okay, I think I saw everybody getting up to question 4 right. All right, so no problem with that. For the last question, I think some of you are working on the right solution, but like for question 5, we said approximately, right? The right solution is to fit a smooth curve through that piecewise constant velocity profile and estimate what is the derivative here. So that gives you du dy, right? And then multiply by the viscosity, it's gonna get you tau. And then divided by half rho is 1.25 kilograms per meter cubed. and UE squared, you get the coefficient. All right. Yeah, I will just briefly give you the answer to the last question during the next lecture, and so I will see you on Wednesday, and you're welcome to come to the office hour. I will be downstairs. All right. Cool. Thank you.